Hello, my name is Arsu, and today we'll be seeing why centripetal acceleration is equal to v squared over r, or in symbols, why a is equal to v squared over r. And v is the circular speed, and r is the radius of the circle, or the circular motion. Now we have a circle and a particle that's traveling around the circle. Now, at this instant, this particle has a velocity that's pointing this way. And the direction keeps changing at every point. So over here, it will be pointing this way. So over here, it will be pointing to the left, and so on. Since this velocity is constantly changing, it's experiencing an acceleration, because change in velocity, or the rate of change in velocity, is equal to acceleration. And this acceleration points radially inward. So at any point on the circle, so if this particle is on any point on the circle, the acceleration it feels will always be towards the center. And we say that this acceleration is equal to v squared over r. So let's see why that happens. Now, we know that acceleration is a rate of change of velocity, and velocity is a rate of change of displacement, or position in this case. So say our point has a position vector at this point. We can represent this as a vector, which is made up of the horizontal and vertical components, and we'll label this px and the vertical py. Of course, this is the radius r. And in vector form, it will be px I hat plus py j hat. So travel px units in the x-axis and then py units in the y-axis. We can't do much with this because, as I said, velocity is a rate of change of position or displacement with respect to time. And we don't really have a time element in this. We can represent px and py in polar form using this angle theta here, because this is a right angle triangle. As you can see, cos theta is adjacent over hypotenuse, so px over r, and sine theta is opposite over hypotenuse, so py over r. And rearranging, you get px is equal to r cos theta, and py is equal to r sine theta. But again, we still don't have a time variable. Well, as the particle goes around the circle, we can see that the angle is changing, and the angle obviously changes proportional to time. So we can say theta is proportional to t. And we can essentially substitute t with theta, but that's not what's happening. But we can think of theta as equivalent to the time. And we won't really be doing any actual differentiation here. This is just a proof by geometry. But it's good to know why the polar form works, or why we need the polar form. Now, we could represent velocity by differentiating this. Since we're doing this geometrically, we'll instead focus on the velocity vector. So now we have the velocity vector here, and like the position vector, we can represent this in first vector form, like this. So this would be, of course, vx, and this would be vy. Obviously, we've seen this before, vx I hat plus vy j hat. And to represent this in polar form, we use this angle here. Why this angle specifically? Well, convention. We usually say if this is an axis, we measure from the positive x-axis counterclockwise. So that's why we use this angle instead of, say, this one. We know that this angle is theta, and this line extends down here. And this is a right angle triangle. We know the internal angles of a triangle add up to 180, and since it's a right angle triangle, this angle and this angle here should add up to 90. So if this is theta, this is obviously 90 minus theta. And we know that this is a right angle, and this angle of a straight line is 180 degrees. Say we label this angle as alpha, maybe this one as beta, where beta is 90 minus theta. So alpha plus beta plus 90 should equal to 180. And working it out, we can see that alpha is indeed equal to theta. So this is theta. And we can represent this in polar form like our position vector. So we get Vy is equal to V cos theta and Vx is equal to V sin theta, where V is the magnitude of the velocity or speed. So this is the circular speed. Now, this cos theta and sin theta can be represented in terms of Px and Py. So we can substitute them in, and we get Vx is equal to V times Py over r, and Vy is V times Px over r. Now we finally get to acceleration, and we know that acceleration is the derivative of the velocity with respect to time. Now the velocity in terms of Vx and Vy with these values, so the velocity vector would be represented by V over r times Py times I hat, and so on. Now, if we differentiate this vector, so dv times dt, we would be differentiating these variables individually. So we get d, dt, we would get this, which is, of course, equal to the acceleration. Now, let's look at each of these individually. And going with the same convention, we can name each of these as ax and this as ay. So ax would be this derivative. And since v over r is a constant, we can take it out of the derivative. So we'd get v over r times the derivative of py with respect to time. Now, the derivative of position is, of course, velocity. Or derivative of displacement is velocity. Now, they've defined Vy as V cos theta. So if we substitute that in, we get Ax is equal to. Now, similarly for Ay, we'd get, and that is the horizontal and vertical components of acceleration. Now, we have the vector components here, but how will we calculate the magnitude? Well, the magnitude of acceleration is the square root of a x squared plus a y squared. And if we write it out, and so if we expand everything out and solve it, so we have v squared over r cos theta, that's whole squared, plus v squared over r sine theta, the whole squared. Expand it, factor out the v power 4 over r squared, and cos squared theta plus sine squared theta is equal to 1. So we'd get this and take the square root of v power 4 over r squared would be v squared over r. And there you have it. We've shown how acceleration is equal to v squared over r in uniform circular motion.